So let's look at how we can compare efficiency in the presence of our assumption that we are only dealing with asymptotic efficiency, right? So we're only looking at properties as n tends to infinity. So in terms of our picture that we saw last time, we said that if we have two functions, and if we have one function which grows very fast, we might have another function which grows more slowly but starts below this, and then we would like to say that this function, say f, is actually better than g, because beyond a certain point, f is below g. So f grows slower than g, although initially it looks like f is growing faster than g. Right? So now we want a way of formalizing this. So what we would like to demonstrate is when is g of n, say, an upper bound for f of n. Okay. Following conventional terminology, we will say that f of n is big O of g of n. So big O of g of n just means that g of n is an upper bound for f of n. Now in our asymptotic world, this really means that we can ignore some initial part, small values of n, and move directly to some particular value n0. And beyond this, we would really like to see that g of n is above f of n. Now this would be very simple, but we have ignored coefficients in this asymptotic thing, so we have to be a little careful. So it's not going to be g of n alone, it's going to be some c times g of n. So some uniform constant factor multiple of g of n is going to dominate f of n for every n which is bigger than n0. So to write this in words, we say that there exists two constants, n0, that is this limit, and c, which is the multiplicative factor, such that for all n bigger than n0, f of n is going to be smaller than or equal to c times g of n. So let's look at an example. Let's try to show that 100n plus 5, for example, is big O of n squared. Right? So what this means is we have to find these two constants c0 and n, n0 and c, such that for every value of n which is bigger than n0, we have c times n squared must dominate 100n plus 5. So the way we do this is to start simplifying this expression to get rid of these things and make everything in terms of n. So we can say that this is less than or equal to 100n plus n, provided n is bigger than or equal to 5, because after n it becomes 5, this is bigger, and this is smaller than or equal to 101 times n, okay, for n bigger than 5, and because n is bigger than 5, this is less than or equal to 101 times n squared, and so we have this property holds provided n0 is equal to 5 and c is equal to 101. Right? So this is one way of showing that 100n plus 5 is big O of n squared, but this is not the only way. We can use a different simplification. So for example, we can say this is also less than 100n plus 5 times n, provided n is bigger than or equal to 1. You can verify that this is true, because 5 into something bigger than 1 will be bigger than 5. And now we can combine this and get this is smaller than 105 times n for n bigger than or equal to 1. And so this is now going to be less than or equal to 105 times n squared for the same reason, for n bigger than or equal to 1. So we have a different way of establishing them for n0 equal to 1 and c is equal to 105. Right? So the important thing to notice is that this choice is not unique. There may be different ways of doing it, but provided you can find at least one n0 and one c such that this property holds, you have this big O property. Now let's see a little more interesting example. So supposing we have 100 n squared plus 20n plus 5. So I want to claim that this is still big O of n squared, even though we have these coefficient terms here of 100 and we have this extra term here 20n plus 5. All that matters, we are going to claim, is the n squared. So again, following our earlier strategy, we will rewrite this. So we can now say that this is smaller than or equal to 100 n squared plus 20 n squared plus 5 n squared. So I multiplied this by n and this 5 by n squared, provided n is bigger than or equal to 1, because once n is bigger than or equal to 1, n squared or n is going to be a larger factor. And now I can combine all these terms and say this is smaller than or equal to 125 n squared. Right? So what we have here is that n0 is 1 and c is 125, and now we have this thing is less than c times n squared, and so this is big O of n squared. So really only the highest term matters, right? So if I have only up to n squared in f of n, then it is O of n squared. It doesn't matter whether it has 20n or 5 or anything smaller than n squared. If it is n squared here, if this is n squared, then it is big O of n squared. So how about a non-example? So let us try to argue that n cubed is not big O of n squared. Okay, so pick any c. Then we can easily verify that c times n squared is going to be smaller than or n equal to n cubed if we have n bigger than c, because once n is bigger than c, then I'll have c times something bigger than c, so I'll have c times d over here, and here I'll have d times d, and d is bigger than c, right? So this is going to be violated for any choice of c. So there's no choice of c for which I can pick an n0 such that n cubed lies below cn squared. So let's look at, just use another piece of notation. So we said that f of n is big O of g of n. So in general, big O of g of n can be also thought of as a set. So it is the set of all f of n such that f is big O of g. Right? So sometimes we will use this notation to just indicate all the possible functions which are big O of g of n. So conversely, sometimes we want a lower bound. We want to say that g of n is a lower bound for f of n. That is, g of n is always smaller. F of n must be at least as big as g of n. And this we write using different notation. We say f of n is omega of g of n. So here the picture is reversed in terms of the curve. So we have this, again, we have some point up to which we are not interested in what happens. And now we'll find that we have this g of n here, and the function that we are interested in always lies above it. Okay? And once again, because we are only looking at orders of magnitude and we're ignoring coefficients and constants and so on, so we'll have a c times this. So here we have a kind of symmetric definition. We say that there exists n0, and there exists a constant c such that for every n which is bigger than n0, we have f of n is bigger than or equal to c times g of n. Right? So this says that c times g of n lies below f of n, so it is a lower bound for f of n. F of n cannot drop below this value. So let's look at an example. Okay, so we claim that although it is not an upper bound, certainly n cubed, for n cubed, n squared is a lower bound. And that's because obviously n cubed is bigger than or equal to n squared for all n bigger than, say, 0 or 1, and for all, and we can just take c equal to 1 as well. Right? So now this is actually not very common in terms of individual functions. So typically this is not, typically this omega notation is not used for a single algorithm or a single function f of n. So usually we will use it for a class of problems. Okay, so we'll say that there is no algorithm. So a lower bound is something says there is no faster algorithm. So for example, we will say that sorting is omega of n log n. So what this means is that we cannot do better than find an algorithm which works in n log n time, where of course the fundamental assumption is that we are doing it in terms of comparisons. Of course, if you use different operations, this doesn't work. So you have to specify what type of operations you're measuring. But we say that sorting as a problem is omega of n log n. So combining these two notions, we can talk about a tight bound. We can say that two functions are actually very closely related in the sense that neither of them is bigger than the other in any appreciable way, and this is written as f of n is theta of g of n. Right? So here the picture is that if I now draw my f of n, then I can sandwich it, okay, again beyond a suitable n0, I can sandwich it by finding two values. So I can have c1 times g of n, and this will always lie above the red line, and I'll have a different function c2 times g of n. So I have g of n is the same function, but I have two constants. C1 times g of n always lies above f of n, and c2 times g of n always lies below f of n. Right? To write it out in words, we say that there exists n0, and now there exists two constants, c1 and c2, such that for all n above n0, we have this c2 times g of n lies below f of n, so it is a lower bound, and f of n on the other hand is dominated by c1 times uh, g of n. Right? So this says that these two functions are really of the same order of magnitude. So here's an example. So supposing we look at a function n into n minus 1 by 2, and we say that this is theta of n squared. So now we have to find these two bounds, right? So we first look at the upper bound. So we want to find this c1 which dominates it. So we can say that n into n minus 1 by 2 is going to be equal to n squared by 2 minus n by 2, which is less than or equal to n squared by 2, because I'm subtracting something here provided n is bigger than 0. Right? So I can take my c1 in this case to be half. So it's going to lie below n squared by 2 for n greater than or equal to 0. On the other side, I can say that this is going to be, this function is going to be bigger than or equal to n squared by 2 minus n by 2 times n by 2, provided that this particular thing is at least 1. So I now need n is bigger than or equal to 2. Right? So that n by 2 will be 1, and so this is going to be bigger than or equal to n squared by 4 for n bigger than or equal to 2. So now I have two bounds. I have one upper bound when n is bigger than 0, one lower bound when n is bigger than 2, and so I can now combine these, and I can say that if I choose in this case n0 to be equal to 2, and I take c1 is equal to half, and I take c2 is equal to 1/4, then I will find that this always lies above 1/4 n squared, it always lies below half n squared, provided n is bigger than or equal to 2. So one thing to realize is that big O, omega and theta are all related. For instance, suppose we know that f of n is big O of g of n, then we claim that in fact g of n is omega of f of n. Why is this? Well, if you look at this definition, it says that there is a constant n0 and a constant c such that f of n is less than or equal to c times g of n for n greater than or equal to n0. This is the definition of big O. Now supposing we take this to the other side, then we get that g of n is bigger than or equal to 1 over c f of n for all n greater than or equal to n0. So if we now take this over here, we can say there exists an n0 and the constant c prime, which is 1 over the old c, such that g of n is greater than or equal to c prime times f of n for all n greater than or equal to n0. In other words, if f of n is O of g of n, then g of n is omega of f of n, and conversely. So this is an if and only if. And similarly, it's easy to see that if f of n is theta of g of n, then we do this in two steps, right? So we prove these constants c1 and c2. So we'll have as two byproducts of this that f of n is both big O of g of n and f of n is omega of g of n. In other words, theta combines the lower bound and the upper bound into one single quantity. So most of the time we focus on big O, because big O is really the only thing that we can compute most of the time. So we mostly focus on saying that something is big O of f of n or big O of g of n. And there is an interesting observation that we need. So let's call it a theorem. So we say that suppose we have that f1 is big O of g1, okay, and f2 is big O of g2. Right? So I have two functions, f1 and f2. f1 is big O of g1, f2 is big O of g2. Then the claim is that f1 plus f2 is going to be big O of the max of g1 and g2. Okay? So this says that if I have big O, then I can add up the function on the left hand side and I can take the max of the function on the right hand side. And this. So why is this useful? So typically if I have a program, okay, so then in my program I might have one block which does something, and then I would follow it up with another block which does something else. Now we could calculate that this one takes f1 time, this one takes f2 time, and I can establish for this that this is O of g1, and I can establish for this that this is O of g2. So now within the function, if I look at the behavior, the total time it takes is f1 plus f2, and I want an estimate for f1 plus f2, and what this theorem tells us is that this is going to be max of G1 and G2. Right? So in other words, if I have a sequence of steps, okay, then the efficiency is upper bounded by the slowest step. The other thing this tells us is that we can break up our algorithm into these kind of blocks, and we can measure the efficiency of each block separately and just look for the worst block, and the worst block will actually be the slowest, and therefore it will dominate the time efficiency of the entire algorithm. So the proof of this property is not difficult. So I have f1 is O of g1, right? So this means that f1 of n is less than or equal to some c1 times g1 of n for all n bigger than or equal to, let us call it n1. On the other hand, we have f2 is O g2, so we have f2 of n is smaller than or equal to some c2 times g2 of n for all n bigger than or equal to n2. Right? So now I'm going to take these two values and I'm going to define n3 to be the bigger of the two. So beyond n1 and n2, so beyond n3, both these properties hold in both these functions. Okay, and we will now also choose, in a likewise, we will choose c3 to be the maximum of the two constants. So we'll say c3 is max of c1 and c2. Right? So now if I look at, for instance, n which is bigger than or equal to n3, then I know that f1n plus f2n, okay, so this is smaller than c1, this is smaller than c2, so this is less than or equal to c1 into g1 of n plus c2 g2 of n, because both these inequalities hold beyond n3. And now this is going to be, since c1 and c2 are both smaller than c3, I can replace these both by c3. Okay, and then I can combine, and this is going to be c3 of g1 of n plus g2 of n. Now I can take the max, so this is going to be less than or equal to c3 times max of g1 of n, g2 of n times 2. Right? So if I take the bigger one and add it up, it's going to dominate g1 plus g2. So either 2g1 or 2g2, whichever. So I can take the max of g1, g2 and pull 2 outside. So now this gives us our thing. So we can now see that this is what I wanted to show. I wanted to show that f1 plus f2 is big O of max g1 comma g2. Right? So I needed to find these constants. So I found a constant. So I have n3, which is the max of n1 and 2, and I have 2 times c3, where c3 is max of c1, c2. So with these two constants, I can show this property, and therefore f1 plus f2, I do have an upper bound as I wanted. So to summarize, so when we are comparing asymptotic complexity of two functions, we have three ways of doing this. So one is to use big O. So when we say that f of n is big O of g of n, then we are saying that g of n is an upper bound. Symmetrically, when we say that f of n is omega of g of n, then we mean that g of n is a lower bound for f of n. And combining these two, we can sometimes say that f of n and g of n are of the same order of magnitude. So f of n is theta of g of n, and this is a tight bound, and both f of n and g of n are essentially of the same order of magnitude. The other important result that we have seen is that if f1 is O of g1 and f2 is O of g2, then from this we get f1 plus f2 is big O of max of g1, g2. And this allows us to focus on the least efficient phase. It says that if we have multiple phases in our computation, then only the least efficient phase determines the upper bound for the overall calculation.